Let's say that I have 3 different chairs and 3 different people who each need to sit in one of the chairs. I can pick any one of those 3 people to sit down in the first chair. So in my first position, I have 3 options as to who can go there. Once that first person sits down, I now have only 2 options as to who can sit in the second chair. And finally, the last person is going to sit in the last chair, so I have 1 option as to who can sit there. These are all of the different ways that we can arrange those 3 people into the 3 chairs. If my blue person takes the first spot, we can have orange and then green. If the blue person continues to be in the first spot, we can switch these 2 people around and have a different order or a different arrangement. If my orange person goes into the first chair, then we can have the blue person and the green person. These 2 can switch seats, or we can have the green person in the first chair, the blue, then the orange. If we switch these 2 around, we now have a different arrangement. So you can see that we have 6 different arrangements in total, and the way that we can get that quickly is by saying we have 3 possibilities for the first position, then 2 possibilities for the next position, and then the last person has to go into the last seat. And remember, in math, and often means that we are multiplying. So if we were to go 3 times 2 times 1, we have 6 different arrangements in which we can arrange those 3 people. Let's say I now have 5 different chairs and 5 objects or people in which to arrange into those spots. I have 5 different possibilities as to who or what can go into that first position. And then once, for example, a person sits down, I now have only 4 possibilities left for as to who or what can go into that next position. And then someone else sits down, I now have 3 possibilities left, and then 2, and then the last person is going to sit down into that last chair. If I multiply them, I have 5 possibilities and 4 possibilities and 3 possibilities and 2 possibilities and 1 possibility. I have 120 different ways that I can arrange those 5 objects. If we are now going to arrange 10 objects, you can hopefully see a pattern here. I have how many possibilities for who or what can go into that first position? Well, you can see that there's 10. Once somebody takes that spot, I now have 1 less possibility for that next spot all the way down until the last person goes into that last position. If we multiply, get your calculator out, 10 times 9 times 8 times 7, etc., we are going to have 3,628,800 different ways that we can arrange those 10 objects. A permutation is an arrangement of objects in a definite order. Each time we change the order, we get a different arrangement or a different permutation. So in order to figure out how many possibilities we have to arrange n number of objects, if each object is different, well, let's see if we can come up with a general rule here. So n represents the number of objects that we have. So in our first example, we had 3 objects. If this was n, what are we doing with n to get down to my next number? Well, hopefully you can see that we are subtracting 1. And then what are we doing with that original amount of objects to get down to this position? You can hopefully see we are now subtracting 2 objects. So n is the number of objects. That's how many possibilities we have for that first spot. And then we have 1 less possibility, 2 less possibilities from the original amount of objects, 3 less possibilities from the original amount of objects as we work our way down that line. This process will continue depending on how many objects we originally started with until the last object goes into that last position. Our second last position, we have 2 possibilities as to what could go there. Our third last position, we have 3 possibilities as to what could go there. Let's take a look at an example, and remember, in mathematics, the word determine means we need to show our process as to how we got our final answer. We are going to determine the number of arrangements. As soon as you see that word arrangement, you have to know that is a permutation. So we're looking for the number of permutations possible using the letters of the word triangle. So we can see that we have 1, 2, 3, 4, 5, 6, 7, 8 different letters. So the first thing we're going to do is actually draw out our positions. And then because we have 8 letters, we have 8 possible letters that could potentially go into that first position. Once we put a letter there, we now have 7 possibilities as to what could go into that second position. And then that process is going to continue. We're going to have 1 less possibility for the next position, one less letter for the next position, one less letter for the next position, one less letter for the next position, until we have two possible letters to go into that second last position, and the last letter has to go into that last position. And then grab your calculator. If we multiply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we are going to end up with the number of arrangements, 40,320 different arrangements if we arrange all 8 letters in the word triangle. N has to be a natural number. It makes no sense to order a negative number of objects or to put fractions or decimals, parts of objects, in order. So anytime we're arranging objects, we always have a positive whole number of objects. N is a natural number. We are multiplying by 1 less than n, 2 less than n. So each time we're going down 1, going down 1, going down 1, until we get to that 3, 2, 1, last object in the last position. Now, if we have a large number of objects, it's awfully cumbersome to be typing this into our calculator every time. So there's actually a quick way we can go about doing this, and it's what we refer to as factorial notation. So it's where we take n number of objects, n being a natural number. If we are consistently multiplying by 1 less each time all the way down to 1, we can represent this entire expression as just n factorial. So it's n with an exclamation point, and we call that n factorial. So we can see that if we start with 8 objects and we are arranging all of them, this is equivalent to saying 8 factorial. So on our calculator, we can press 8, and then if we go into the math menu, we're going to arrow over to the probability menu. Now you could go on the right arrow, right arrow, right arrow, but it's actually faster if you press the left arrow. And then you can see number 4 is that exclamation point. So we're going to press number 4, and we have 8 factorial, enter, and you can see we get the same value as if we were to type out 8 times 7 times 6, etc. So the factorial notation is a quick way that we can get the product of those numbers. There is, however, a limit to what your calculator can do. If we had 100 objects, let's say, and we were to put them in order, all of them down to 3, 2, 1, if we have 100 factorial and press enter, you can see that our calculator says overflow. It's too many numbers for the calculator to handle. So we have to have another way that we can go about this. Grab your calculator because we're going to practice entering the factorial notation, beginning with 10 factorial. So you can type in 10. These are the steps we're going to enter to get to that exclamation point, and you should be getting 3,628,800 as your answer. Now, if we see something like this, 5 times 4 times 3 times 2 times 1, you should recognize that is 5 factorial. We are beginning with 5 objects. We are going down 1 each time until we get to that 3, 2, 1. Last object is 1. So that is 5 factorial. We can enter that into the calculator and get a value of 120. This one here, we have 9 times 8 times 7 factorial. So that factorial tells me I'm then going to have 6 times 5 times 4 times 3 times 2 times 1. And then because if I were to go this way, 8 is the natural number that we would add on if we're going to the left, 9 is the one we would add on. This expression is equivalent to if we were to just say 9 factorial. So we have 7 factorial times 8 times 9 is just 9 factorial, which has a value of 362,880. Now, what about 0 factorial? What happens when you put 0 factorial into your calculator? And you might notice we get a value of 1. Well, if we arrange 0 objects, how do we get one arrangement out of that? You can think about set theory. There is only one way to arrange no objects. We end up with an empty set. There's nothing in it. So 0 factorial is 1. If we are adding different factorial notations together, your calculator can just do order of operations. So we would work out 5 factorial plus 4 factorial plus 3 factorial. If you put that into your calculator all as one expression, you will get a value of 150. Now, if you're dealing with fractions, remember your calculator is not great with fractions. So you have to tell the calculator that in order to get the correct answer, we need to bracket the denominator. So we're going to have 12 factorial divided by the product of 9 factorial times 3 factorial. Your calculator can do that, but I want you to see another way that we can go about this. So we know 12 factorial is just the product of 12 times 11 times 10 times 9 all the way down to that 3, 2, 1. If I take 9 factorial, I'm actually going to line that up where I have 9 times 8 times 7 times 6 times 5, etc. And then just because I ran out of room, 3 factorial, let's put that over there. Now, if we were to divide, because we are multiplying every one of these numbers across here, so if I were to go 9 divided by 9, I would get a value of 1. 8 divided by 8 is equal to 1. 7 divided by 7 is equal to 1. So hopefully you can see that we're taking this whole 9 factorial piece and we are dividing by this 9 factorial piece, and everything along here is going to end up canceling out. And then we can take a look at what's left. I can go 12 divided by 3 and get a value of 4. I can go 10 divided by 2 and get a value of 5. And so what we're left with in the numerator is 4 times 5, which is 20, times 11, divided by that 1. So we can go 4 times 5 times 11, or 20 times 11, is 220. So you can either put this into your calculator. Remember, you have to bracket the denominator and get the value of 220. But because we're going to throw some algebra into here, you also need to have an understanding as to what's happening. So each one of these, when we divide out those factors, we're getting a value of 1 every time. And then we can take a look at what's left, and we can also divide some of those factors out to make these numbers more manageable. This is something that we could do mentally. All right, so here comes the algebra. Let's throw some variables into here. So if we are asked to simplify the expression, can we take what we're given and get it into a simpler form? So we start with n objects. We go down 1, we go down 1, we go down 1, and that process will continue until we get to that 3, 2, 1 last object in that last position. That exclamation mark tells us that we are going to keep going. So we can simplify this by saying n represents the number of objects we have, because we are going down 1 each time, and that process will continue until that 3, 2, 1. We can just say this is equivalent to having n factorial. Now, we do also need to state a restriction because we have some variables here. So I know that n has to be a natural number, and because 0 factorial will give me 1, then n can be equal to 0. So I'm going to take each of these factors, and let's take a look at what the restriction would be. So I know for this one, n has to be greater than or equal to 0, because 0 factorial is possible. And then similar to how we did restrictions with radicals in the previous course, we're now going to take this factor, n minus 1, and set it so that it is greater than or equal to 0. And then when we isolate n, we're going to see that in order to make this factor a natural number or 0, n will have to be greater than or equal to 1. Same thing here. So we're going to take this factor, we're going to set it greater than or equal to 0, and then we're going to isolate n, and we're going to see that n has to be greater than or equal to 2, and the same thing with the last factor that we're given. So we're going to take this factor, we're going to set it greater than or equal to 0, and we're going to isolate n, and we're going to see that n must be greater than or equal to 3. Now, which of those restrictions do we choose? And again, similar to last year, we can plot those on a number line. We are looking for the one that satisfies all conditions. I do not want to choose 0, because if I choose 0, that's okay for this one, but if I were to put a 0 in for n here, 0 minus 3 is negative 3. Well, I can't have negative 3, I can't have a negative number of objects, so that's not going to work. So if we take n is greater than or equal to 0 and put that on a number line, n can equal 0, we have that closed circle, or it's going to be every natural number greater than that. N can equal 1, or it's going to be every natural number greater than that, and so on. We are choosing the one that satisfies all. So you can see that if we go down here, that 3 is going to allow us to satisfy each of those conditions. So if I put a 3 in for n, this will be a natural number greater than or equal to 0, as will this factor, as will this factor, as will this factor. So anytime you're doing the restrictions with factorial notation, if you take a look at the factors that we are given, anytime we go to isolate n, you can see that it's always going to be our smallest given factor that when we rearrange it is going to be that restriction that satisfies all conditions. So we are looking for what is the restriction on the smallest factor, in this case n minus 3, and that's the one that will satisfy all. So if n is equal to 3 or greater than 3, each one of these numbers is going to be a natural number or 0 factorial, which is possible. All right, so in our next one here, you can see that we are given 4 different factors. Check to see, are we going down 1 each time? So we begin with n plus 3. If I subtract 1, I'm going to get n plus 2, subtract 1, n plus 1, subtract 1, we have n plus 0, and then factorial. So that means we're going to keep going until we get to that 3, 2, 1, because we don't know the value of n. If n is 10, this is 13, then 12, then 11, and so on. So because we are going to continue that process, this is going to be equivalent to just just n plus 3 factorial. So we're going down 1, going down 1, going down 1, and that's going to continue until we get to that 3, 2, 1. Now, of the 4 factors that we are given, which one is our smallest factor? Well, we can see that's just going to be this n. So n must be greater than or equal to 0. That's my restriction, and then that's going to satisfy all. So if n is 0, 0 plus 3 is 3, that is a natural number. Now, when we have something written in fraction form, similar to what we did with that previous example where we had 12 factorial divided by 9 factorial times 3 factorial, we want to begin by writing out our factors, beginning with the one that we see, this n plus 1. So we're going to start with n plus 1. We're going to go down 1, down 1, so I'm subtracting 1 to get to n plus 0, subtracting 1, n minus 1, subtracting another 1, n minus 2. That's going to continue until we get to that 3, 2, 1, last object in the last position. Now, I'm dividing by n minus 1 factorial. So I'm going to line it up. So we have an n minus 1 here. So let's go ahead and line this up down here. So then I'm going to subtract 1 to get to n minus 2, and that's going to continue until I get to that 3 times 2 times 1. So what's going to happen is n minus 1 divided by n minus 1 is 1. N minus 2 divided by n minus 2 is 1. So everything along here is going to cancel, and I'm going to be left just with this n plus 1 times n. So that is my simplified answer. Now notice there's no exclamation point here because we're not continuing on. Every other factor cancels out, or we end up with just 1 when we divide them. So these are the only 2 factors that we are left with. That is our final answer. Now, before we cancel anything, we should actually be doing the restriction. So take a look at the 2 factors that are given to us, which is the smallest, and we can see n minus 1 is the smallest. So we're going to set that greater than or equal to 0, and our restriction will then become n must be greater than or equal to 1. And we can even just maybe write that here. So if we take that smallest factor, n minus 1 must be greater than or equal to 0, then in order to isolate n, what we're doing is adding 1 on, and that's how we get that restriction. All right, so why don't you pause the video and actually try this last example, and then come back and we'll see how you did. And welcome back. So again, remember, we're going to take this factor that we see and we're going to write that down first of all, and then we're going to go down 1, and that's going to continue until that 3, 2, 1. We're going to take this first factor that we see. If possible, we're going to line it up under something we know that will cancel. And again, that's going to continue because of that exclamation point down to that 3, 2, 1. So we know when we go to divide these out, n minus 4 divided by n minus 4 is 1. Everything along here we're going to divide out, we're going to get a value of 1. So we are left with only 2 factors left in the numerator, so that is our answer in factored form. Now if you wanted to FOIL this out and get n squared, negative 3n minus 2n is negative 5n, plus 6, that would be okay as well, but we can just leave the answer in factored form. And again, before we cancel anything, we should be doing the restriction. So we can see that of these 2 factors given to us, this is our smaller one. So we're going to take that n minus 4 and we're going to set it so that it's greater than or equal to 0. And again, we can go ahead and write that in here. So n minus 4 has to be greater than or equal to 0. And when we go to isolate that n, we're going to add 4 to bring that to 0, add 4, and then we can see that we have a restriction. If n is equal to or greater than 4, then each of these factors will be 0 or a positive number. And finally, we're going to solve some equations that involve factorial notation. So the first thing that you want to do is get rid of the factorial notation. So we're going to actually begin with the factor we see, and we're going to start writing them out. So in the numerator, we have n factorial. I'm going to go down 1. That's going to continue until I get to that 3, 2, 1. And then in the denominator, we have n minus 2 factorial. So I'm going to line that up, n minus 2, and that's going to go down to 3, 2, 1. Because now I know n minus 2 divided by n minus 2 will cancel out. That's going to give me 1. Everything along here is also going to divide out, giving me 1. So now we've simplified it. We've taken it out of factorial notation, and we are left with n times n minus 1 equals 90. So we can go ahead and write that out. And then in order to get rid of the brackets, we're going to take that n, we're going to distribute that in. So n times n is n squared, n times negative 1 is negative n. And you can see see that we now have a quadratic equation. So we're going to bring everything over to the side where that squared term is positive. And then remember to the last course, we can solve a quadratic equation either by factoring or by using the quadratic formula. Now, if you're not sure what the factors are, you can use the quadratic formula. However, we know that n has to be a natural number, so these will factor. So we're going to multiply a times c together. So what are two numbers that are going to multiply to negative 90 and then add to that b value of negative 1? We can see it's negative 10 and 9. And then we're going to reverse FOIL. So n times n gets us back to n squared. Remember, these are your outside and inside products. So 1 times 9 is going to give us that one factor, and then the inside product, n times negative 10, gives us that other factor. Set each factor equal to 0. So in this factor, what will make this 0 is if n is positive 10. Here, if n is negative 9, that's also going to make that equal to 0. Now, before we do anything, we should be doing the restriction, which I actually did, but I forgot to uncover it. So we can see that the smallest factor here is going to be n minus 2. So set that factor so it's greater than or equal to 0. N has to be greater than or equal to positive 2. We can see that negative 9 is not greater than or equal to positive 2. So negative 9 is extraneous, leaving us with one solution of n is equal to 10. And as always with algebra, we're going to check that answer. So we're going to take, if n is equal to 10, we're going to substitute it back in the place of n. So we're going to have 10 factorial. 10 minus 2 is 8 factorial equals 90. And then I know that 8, 7, 6, 5, 4, etc. is going to cancel it with the 8 factorial on the denominator, leaving me just with 10 times 9 in the numerator. 10 times 9 is 90, so the left side equals the right side. We know that 10 is an answer. We know that n has a value of 10. And again, you can always use your calculator if you wanted to store it as the variable. Substitute it back in, but make sure you check, does the left side equal the right side? In our next one here, we also have an algebraic equation. We have a left side and a right side. We have to solve to determine the value of n. So because it's in factorial notation, first thing we should be doing is the restriction. So I'm going to take a look and I'm going to say, okay, this is my smallest factor. So n plus 2 has to be greater than or equal to 0. So that means n has to be greater than or equal to negative 2. And then the first thing we want to do is take this out of factorial notation. So we're going to begin with the factor we see, n plus 4. We're going to write that down, and then we're going to minus 1, minus 1. That's going to continue till we get to that 3, 2, 1. And then in the denominator, we have n plus 2. So we're going to line that up, factorial. So then again, we're going to go down 1 until we get to that 3, 2, 1. And then on the right-hand side, we have equal to 6. So we are going to divide out everything that's going to cancel out, and that's going to leave us just with two factors, n plus 4 times n plus 3 equals 6. So now I can get rid of those brackets by foiling. So I'm multiplying two binomials together. So I'm going to have n squared, 3n plus 4n is 7n, and then 4 times 3 is 12. And then I can see that this is a quadratic equation. So I'm going to bring everything over to the side where it's positive. So we're going to subtract 6 from each side to make the one side equal to 0. And then I can solve this by factoring. I know it's factorable because n has to be a natural number. Are there two numbers that will multiply to 1 times 6, which is 6, and add to 7? Well, I know 6 times 1 is 6. 6 plus 1 is 7. So I'm going to go ahead and factor that. We're going to set each factor equal to 0. So n is going to be negative 1 or n is going to be negative 6. But then we have to check it against the restriction. N has to be greater than or equal to negative 2. So I know that this is going to be extraneous. N is equal to negative 1, but I'm going to check that. If I substitute this negative 1 back in for n, negative 1 plus 4 is positive 3 factorial, negative 1 plus 2 is 1 factorial equals 6. Well, I know 3 factorial is 3 times 2 times 1. 1 factorial is just 1. I can divide out the 1s, and then 3 times 2 is 6. The left side equals the right side, so negative 1 is a solution to this equation. And finally, we have this equation here. Because I have two factors containing variables that are written with factorial notation, I want to try to write them so that they look like a fraction. So I'm going to actually divide one of them by the other one. And then before we do that, we can state the restriction. So I can see that of those two factors, this is my smallest one. So I know that n is going to have to be greater than or equal to positive 3. All right, so now I've got the factorial part looking the way the previous questions did. I can also go ahead and divide out that 5. 60 divided by 5 is just 12. 12. And then at the same time, I'm going to take this out of factorial notation. So we're going to begin with the factor we see, go down 1 until we get to that 3, 2, 1. And then this factor I see in the denominator, n minus 3, we're going to begin with that factor, write down what you see underneath the one that's going to divide out with, and then that's going to go down to 3, 2, 1. And then again, we're going to cancel. All of this will cancel out, leaving us just with those two binomials equal to 12. I'm now going to FOIL those two out, and lo and behold, we have a quadratic. Because my squared term is positive here, I'm going to move everything over. So I'm going to subtract 12 from the constant term on the left side, and that's going to give us something that is factorable. So what are two numbers that multiply to negative 10 and add to negative 3? Well, we have negative 5 and positive 2. Set each factor equal to 0, and then check it against your restriction. So n has to be greater than or equal to positive 3. Negative 2 is not going to be greater than or equal to positive 3, so that's extraneous. We think the solution is n equals 5, but we're going to verify that. So we're going to substitute it back into the original equation in the place of n. So we have 5 minus 1 is that 4 factorial times the 5, and then 5 minus 3 is that 2 factorial times the 60. And you can put this into your calculator to see what you get on each side, but the left side does equal the right side, so that is our solution.